So what we're going to talk about today is this process called the partial fractions decomposition. What that means is I want to take a rational expression like this one here, and this is obviously normally how we think of rational expressions, right? One polynomial divided by another. And what I want to do is I want to split it up, right? I want to split it up into the sum or difference of two smaller polynomials. For example, this guy here is equal to this. Okay, now you can reasonably ask, why on earth would I want to do such a thing? The first polynomial was perfectly good, the first rational expression. Well, there is a reason. In calculus, integrating that original polynomial, this one, is really hard. Integrating these two guys, on the other hand, is actually really, really easy. And that's why we want to be able to do this. This is, if this is used anywhere else, I'm not saying it isn't, but in 25-ish years of teaching math, that is the only place I have ever seen this come up. All right, so this is why we often teach this in pre-calc classes. We're kind of looking ahead. Most of the students in pre-calc are eventually going to go on to calculus. And if we can cover this here, it's one less kind of diversion into algebra that calculus teachers need to take when they eventually get to this part. So there are four different examples we're going to think about here. And it really is based on the denominator. So the denominator that's going to drive this whole business. And I've kind of outlined them here, and it's math speak, and obviously we're going to look at some examples. But when I say Q has only non-repeated factors, that's something like x minus 1 times x plus 2, right? It has all linear factors, and each of them only appears once. Repeated linear factors, that would be something like x minus 1 squared times x plus 2. Now that x minus 1 factor, it's in there twice. That's what we mean by a repeated factor. Non-reducible or irreducible quadratic factors. That's a quadratic factor that you can't factor down into linear ones. For example, something like x squared plus 1 times x minus 2. That x squared plus 1, it can't be factored, just stick into real numbers. So that would be an irreducible quadratic factor. And repeated ones, it's the same as the linear case. That would be if we have something like this. Okay, so we're going to treat each one of these separately. All right, so first, let's look at the case where there are non-repeated linear factors. Each linear factor appears exactly once. And here's kind of what I'm going to do. I'm going to rewrite this as all of these A's, all of the capital A's on top, these are just numbers, right? And down here on the bottom, these are just the factors of Q. Okay, so yeah, okay, that's how I want to write it. What am I going to do to get there? All right, well, I think this is one of those math things where it's easier if we just do some examples. All right, so I got my expression here, and step number one is just going to be to factor everything. All right, the numerator can't be factored any further. The denominator is x plus 3 times x plus 1. All right, now my rule right from the previous slide says I want to rewrite this as a over x plus 3 plus b over x plus 1. So the big question now is, how do I get a and b? Right? Once I find numbers for a and b, I'm home free. Well, here's what I'm going to do. I'm going to add these two rational expressions on the right-hand side together. How do you add fractions? Well, I got to have a common denominator. Right? So let's see. I'm going to make this, I'm just looking at the first one. I'm going to multiply the denominator by x plus 1. I'm going to multiply the numerator by x plus 1. Right? That was the denominator from the other side. Now I'm going to do the same thing with the right-hand one. I'm going to multiply the top by x plus 3 and the bottom by x plus 3. Right? That was the numerator from the first part. And now that the denominator from the first part, excuse me, now the denominators are the same. Now I could just add these two things together. This is ax plus 1 plus bx plus 3 over that common denominator. Okay, great. Now let's clean up that numerator. Let's distribute to get rid of the parentheses. Ax plus a plus bx plus 3b over that common denominator. And now look, I'm going to rearrange and do some factoring. Let's put the two x parts together. That's a plus b times x plus a plus 3b all over that common denominator. All right, now let me write the other part in. Let me put the left-hand side back. X plus 2 over x plus 3 times x plus 1. Okay, well, let's do this next. Let's get rid of the denominators. Right, multiply both sides by x plus 3 times x plus 1. Multiply and multiply. And that's just going to clear the denominators out. All that's left is the numerators. X plus 2 equals a plus bx plus a plus 3b. Excellent. This is progress. Okay. The only way two polynomials can be the same is if all of their coefficients are the same. The coefficients of the x squared terms are the same. The coefficients of the x terms are the same. The constants are the same, and so on. So that's what I'm going to do here. I'm going to set the coefficients of the x terms equal to each other. That's a plus b equals 1. And I'm going to set the constant terms equal to each other. That's a plus 3b equals 2. And now look at where I ended up. That's a system of linear equations. And we have techniques for solving systems of linear equations. I'm going to go, because it's going to be pretty easy to do so, I'm going to go with the substitution method. Solve the first one for a. A is equal to 1 minus b. Now substitute that into the first equation. 1 minus b plus 3b equals 2. Move the 1 over. Let's see, 3b minus b, that's 2b equals 1. B equals 1/2. There you go, we're halfway done. Right, now take this, put it back into that original one there. A equals 1 minus 1/2, which is also 1/2. That answers my question. Take these a and b values, put them back into there, and I get my answer. 1/2 over x plus 3 plus 1/2 over x plus 1. But please don't leave it there. Let's clean this up a little. Just to fix the fractions. This is 1 over 2 times x plus 3 plus 1 over 2 times x plus 1. And I can go just a little further. 1 over 2x plus 6 plus 1 over 2x plus 2. And that's it, right? There, that is my partial fractions decomposition of the original polynomial. Okay, let's try another one. What do we do if there are repeated linear factors? Well, I'm really going to do the same thing, right? Only now, instead of having one term for each factor, I'm going to have more than one, right? So you see I have a over x minus a, and I have a second number over x minus a squared. So it's kind of like each repetition of the factor gets its own term in the decomposition. So let's see how we can do that. Again, it's easier if we go to examples. So this is x squared plus 1 over x times x squared plus 4x plus 4, which is x squared plus 1 over x times x plus 2 squared. And you see, there's my repeated factor, my repeated linear factor. So how am I going to break this up then? How am I going to decompose this? Well, this is going to be a over x, and that's it, because that x appears once, just like we had in the previous examples. Then I'm going to have plus b over x plus 2 plus c over x plus 2 squared. And now I'm back to the same process, right? The flow is going to be the same once we get to this point. Write everything as one fraction, multiply out the numerator, set the coefficients of the numerator equal to the corresponding coefficients in the numerator of the original. Okay, so obviously we've got some work to do now, right? We need to do our common denominator. So let's see. What's my common denominator going to be? It's going to be x times x plus 2 squared. So I have to add an x plus 2 squared to the first term. I have to add both an x and an x plus 2 to the middle term. And the last term just gets an x. Okay, now it's combining everything together and doing a lot of really careful algebra. Okay, so let's see. This is a times x plus 2 squared plus bx times x plus 2 plus cx over x times x plus 2 squared. All right, so I've got to multiply this x plus 2 squared out. That's a x squared plus 4x plus 4. Then distribute the bx plus bx squared plus 2bx plus cx, still over that common denominator. Now distribute the a. Right, this is ax squared plus 4ax plus 4a plus bx squared plus 2bx plus cx. Whew. Okay, now let's group some stuff. The x squares was still over that common denominator. All right, so let's group the x squares. A plus bx squared, and that takes care of those two. Then we'll group the x's. There's several of them. So this is plus 4a plus 2b plus cx and plus 4a. That's it. We're done. Over this thing. And that still equals. Now let me go ahead and write it back in. X squared plus 1. This is the original. Over x cubed plus 4x squared plus 4x. Now we can set the coefficients equal. The x squared coefficients are 1 and a plus b. The x coefficients are 4a plus 2b plus c and 0. And look, we're going to get off easy here. The constant terms are 4a and 1. So a is just 1/4. We got off easy, right? Now just start substituting. I'm going to put 1/4 into this one. 1 is equal to 1/4 plus b. Subtract 1/4 from both sides. And b is 3/4. All right, now put both of these numbers into the middle equation. And we get 4 times 1/4 plus 2 times 3/4 plus c equals 0. So let's see, this is 4 times 1/4, that's just 1. 2 times 3/4 is 3 halves, plus c equals 0. 1 plus 3 halves, that's 5 halves. So c is -5 halves. And that's my answer. Let's put these in. Remember where we came from here. We're going back to here and putting a, b, and c in there. So that's 1 over 4x plus 3 over 4 times x plus 2. I should have started lower. Minus 5 over 2 times x plus 2 squared. And that's it. That's our decomposition. Some people might insist you multiply stuff out, multiply out those denominators. I'm usually okay if you leave it like it is. Again, I'm looking ahead to that calculus class, and when you're doing this in calculus, you're going to want the factored versions because those are going to be easier to work with. Okay. Let me give you one. Pause. Go ahead and pause the presentation, right? See if you can't break this one down into its decomposition. All right, so let's see. First, let's do some factoring. This is x times x plus 2 over x to the third times x squared minus x minus 2. And this is nice. I'm thinking I'm going to get some canceling going, which is nice. It's going to reduce the number of terms that I have in the decomposed version. So this is, let's go ahead and cancel here. This cancels with one of these and leaves a 2. So this is x plus 2 over x squared times x minus 2 times x plus 1. Darn, I was hoping I'd cancel that x plus 2 also. But I didn't. We're stuck with it. So here's where we end up. This is equal to a over x plus b over x squared plus x minus 2, plus c over x minus 2 plus d over x plus 1. Okay, what's my common denominator? It's going to be this denominator that was over here on the left-hand side, right? Ultimately, that's going to be my common denominator. So what do I have to do to get there? This is a x times, okay, look, x minus 2 times x plus 1, which I already knew was this. So let's go ahead and write that in there instead. X squared minus x minus 2. I'm trying to take a few shortcuts here. Over, and look, when I do these, I'll admit, I start to get lazy. I really don't want to write that common denominator over and over and over again. So I'll just get cheap and put common denominator. So then this is plus b times x squared minus x minus 2 over the common denominator plus cx squared times x plus 1 plus dx squared x minus 2. Okay, multiply stuff out. So this is a x to the third minus ax squared minus 2ax plus bx squared minus bx minus 2b plus cx to the third plus cx squared plus dx to the third minus 2dx squared. See why I'm not writing that denominator out? I've got enough trouble writing out the numerator. Okay, so now, okay, let's regroup. X to the third, there's two of them. Ax to the third plus cx to the third. Now the x squareds plus cx squared. Whoa, sorry, I lost one. There was a dx to the third over there too. Plus dx to the third. Let's get that in there. Now we'll do the squares. Plus cx squared. I really want to put a positive one in front. plus bx squared minus 2dx squared minus ax squared. Oh boy. Okay, that's the x squareds. Now the x's, minus 2ax minus bx minus 2b. And all of this has to equal, well, still, there's no point, right? Sorry, I was going to jump ahead, but I'm not there yet. Over the common denominator. Okay, so now at this step, let's clear the denominators. We're going to multiply both sides by them and just look at the tops. All right, so the tops are x plus 2 equals a plus c plus d x cubed plus c plus b minus 2d x squared plus minus 2a minus bx minus 2b. Wow. Okay. So what do we get here? I'm quickly running out of room. But let's see. Minus 2b, that's the constant term, has to equal the constant term on the left side, and that's 2. Awesome. We got off easy. B is negative 1. All right, now keep going. Right now, let's do the x terms. Minus 2a minus b has to equal 1. But I already know what b is. Right, b is negative 1. So this is negative 2a minus 1 equals 1. That's minus 2a plus 1. Well, that's nice. Subtract 1 from both sides. Minus 2a equals 0. So a is equal to 0. Well, that came up pretty good. All right, how about the next one? C plus b minus 2d equals, that's the x squared term, right? There is no x squared term on the left-hand side, so that's 0. And a plus c plus d also equals 0. All right, now let me put the numbers that I know in here. All right, I know a is 0, so c plus d is 0. I just put 0 in there for a. Now I go to the middle one and put negative 1 in there for b. C minus 1 minus 2d equals 0. So C, okay, time out. I got a system of equations here now, right? I've got something with C's and D's and something with C's and D's. I need to solve this. I'm thinking substitution. So I'm going to go ahead and solve this equation for C. This is C equals 1 plus 2d. Now let's substitute that into the other one. 1 plus 2d plus d equals 0. 3d equals negative 1. D is negative 2/3. Excellent. Now put that back into here. C is 1 plus 2 times negative 2/3. That's 1 minus 4/3. That's negative 1/3. And that's it. That's it. Now I can write my answer. And I'm hugely out of room, so I'm just going to squeeze it in here in the middle. This is, a is 0, so that term just goes away. So this is minus 1 over x squared minus c is negative 1/3, right? So minus 1 over 3 times x minus 2 minus 2 over 3 times x plus 1. And that, right in the middle of everything, that is my final answer. Okay, so those are the linear factors. What do you do if there's a nonlinear factor? Well, I want you to kind of think about what we did with the linear ones, right? If there was a first degree factor in the denominator, I put a 0 degree factor, if you will, in the numerator, right? I put something that was 1 degree smaller. I'm going to do the same thing with the quadratics. if there's a quadratic factor in the denominator that I can't factor further, that I can't break down to linear factors, then I'm going to put a linear factor in the numerator in my decomposed version. All right, so let's look at an example, see how this works. That denominator here, it factors, right? It's the sum of two cubes. This is going to become 2x plus 1 over x plus 2. You remember how the sum of two cubes factors. This is x squared minus 2x plus 4. Okay, and remember the thing about factoring the sum and difference of two cubes, that second part, it never factors further. Not into integers anyway. So that's going to be our irreducible quadratic factor. All right, now I can rewrite this. This is a over x plus 1 plus b, excuse me, this is our new one, right? bx plus c over x squared minus 2x plus 4. See, I'm messing up today. That should be an x plus 2. So it matches the left-hand side. I was looking at the 1 up in the numerator. Okay, we already know the common denominator. The common denominator is going to come from the original denominator. So I have to multiply the top and bottom of the first fraction by x squared minus 2x minus 4. And the top and bottom of the second fraction by x plus 2. Awesome. Now I can make the numerators equal. And I'm gonna go ahead and multiply these out as I do. First, distribute the a. This part is ax squared minus 2ax minus 4a plus bx squared plus 2bx plus cx plus 2c, all over that common denominator. And now I got to group stuff. Let's bring the x squareds together. There's two of them. A plus bx squared. Let's bring the x's together. Plus cx minus 2ax plus 2bx. That's those two. Minus 4a plus 2c. Okay, so now we're almost there. I just have to group those, factor an x out of the middle part, right? And let's get rid of the denominators. Multiply through by the common denominator. We end up with 2x plus 1 equals a plus b x squared plus c minus 2a plus 2bx minus 4a plus 2c. Okay, now what? Well, let's see. A plus b has to equal 0 because there's no x squared term over here. Then c minus 2a plus 2b, that's the x coefficient, so that has to be 2. And minus 4a plus 2c has to be 1. Okay. Now what? Well, here's what I'm going to do. I'm going to eliminate the b. This is the part where you got to be a little creative. I'm going to eliminate the b from the second equation, because when I do, that'll give me an equation that just has a's and c's, and that matches what's in the last one. So what did I say? I'm going to eliminate the b's, right? B is minus a, so this becomes c minus 2a plus 2 times minus a equals 2. C minus 4a equals 2. Okay, this is actually coming out nice. Let's do elimination. All right, I'm going to multiply this equation by -1. It'll become 4a minus c equals -2. Add these together. The a's cancel. C is equal to -1. Excellent. That's what I needed to see. Okay, so if C is equal to -1, put that back into here. I'm really running out of room, so I'm going to have to write a little small. -1 minus 4a equals 2. Add 1 to both sides. It won't even let me. I'm too close to the bottom. A is -4/3. And if A is -4/3, then B is -4/3, which is +4/3. And that gives me my decomposed version, right? This is -4/3 times x plus 2 plus, let me make sure I get these right? I need B, which is 4/3. So that's 4/3 x, and C is -1, -1 over x squared minus 2x plus 4. And that's my answer. I would stop there. You really don't need to clean that up any further. Okay. Last one. I told you 4 cases, right? If there are repeated irreducible quadratic factors, you treat them exactly the same way that you treated the irreducible linear factors. They're just going to appear more than once, right? Depending on what that exponent is. All right, so let's do one. I have this marked as practice. I know this is the first one. If you like, you can go ahead and pause this, right? You can give this one a try, right? I've already factored a little bit in the denominator, right, just to make things a little easier. Okay, so x squared plus 2 doesn't factor. Not with integers anyway. So what am I going to get then? This is x cubed plus 1 over x squared plus 2 squared equals ax plus b over x squared plus 2 plus cx plus d over x squared plus 2 squared. Okay, so you see this one, it isn't too bad. That last rational expression actually already has the common denominator. Right? So all I need to do is multiply this first one, top and bottom, by x squared plus 2. And now the denominators are the same. And I can combine the numerators. I'm going to multiply this one out as I do this. This is ax to the third plus bx squared plus 2ax plus 2b plus cx plus d, that comes from the second one, over that common denominator, which I'll now get rid of. I multiply both sides by x squared plus 2 squared. And you get the numerator of the left side, that's x cubed plus 1, equals the numerator of the right side. And I'm going to do a little factoring if I can here. Ax cubed plus bx squared plus, let's put these x terms together, 2a plus cx plus 2b plus d. And look, this is going to come out unusually nice. The coefficients of the x cubed terms are a and 1. There you go. We got one of them already. And look, the x squared terms are just as nice. the coefficient of the x squared terms are b and 0. It's not usually quite this easy. It's coming out nice for us. Then let's see, 2a plus c equals 0, and 2b plus d equals 1. All right, so let's see, what do I know? I know that a is 1, so let's put that in here. 2 times 1 plus c is 0, so c is negative 2. And b is 0, so this is 2 times 0 plus d equals 1. And d is equal to 1. That actually came out to be one of the nicer ones. Now let's write it in here and get the final answer. This is this is x over x squared plus 2 plus, let's see, negative 2x plus 1 over x squared plus 2 squared. And that's it. That's my final answer. All right, so those are all four cases for this partial fractions decomposition. Obviously, we could go further. If you have an irreducible cubic, you would put ax squared plus bx plus c in the numerator. We're not going to go that far. Okay, we're going to stop just with irreducible repeated quadratic factors. And again, I want to take a step back and think about this. They're not really hard, I don't think, per se. They're kind of long, right? There's a bunch of steps. You got to play with the rational expressions, common denominators. Then maybe you've got a system of equations you have to solve, right? But you know those techniques. It's just kind of long and messy. So when you're doing these, couple of things. First, be persistent. You know it's going to take multiple steps. You know it's going to take a good half a page to maybe even a whole page to do this. Second, go slow and resist the urge to skip steps. Right? Skipping steps is when there's this much stuff going on. That makes it really easy to accidentally miss something. And third, be neat, be organized. If you start letting your stuff wander all over the page, it's easy to lose track of where you are, easy to misplace something that you needed, right? Organization is really going to help you out here.